Hello, welcome to the 13th class of this course. Let me first summarize what we did in past few classes. So we started with Legendre differential equation. We solved it, we got the general solution. Okay, so general solution is basically linear combination of two linearly independent solutions, right? That is y even and y odd. And now depending on integer values of a, we truncated these infinite series and we got polynomials. Those we are calling the Legendre polynomials, and those are denoted by PLX, okay, where L is going from 0, 1, 2, 3, and so on. And then we showed that using Rodriguez formula, we can also generate the same Legendre polynomials. After that, we showed that using generating function, also those Legendre polynomials can be derived, okay. And in the last class, I showed you some recurrence relations related to this Legendre polynomials, okay. So in this class I will talk about some applications of this Legendre polynomials. So for example, if we have inverse square forces, so that means inverse square forces means, for example, let's consider a electric charge, okay. So let's say this is our coordinate system. This is our coordinate system in 3D. Okay. This is our origin O, okay. And let's say here there is a charge Q, right? And distance from the origin, for example, let's say small r, okay. And here, let's say we want to derive the electric field, or let's say there is a unit charge here and we want to know the force on this charge due to the presence of this charge, okay. So, or we want to know the field at this point, okay. This point is at a distance r from the origin, okay. And the distance between these two these 2 points, so this is called the source of the field, and this is where we want to detect, we want to measure the electric field, or basically the effect of electric field, that is the force on a test charge, for example. So that, let me call it D, okay. So I can write D as then R minus R, okay. And so D, let me say D is the magnitude of D vector, okay. So these notations, I mean, it follows basically for R and capital R and small r also, okay. So now if I write the force, then the force is, or the electric field is basically some constant K times the source charge, that is capital that is small q, okay, this charge, because of which we want to know the electric field here, or let's say there is a test charge and the force on this test charge, okay. So then the electric field will be d square times d hat. The d hat, what is d hat? D hat is the unit vector along D, okay. Or if I am interested in only the magnitude, then it is just K Q by D, right? Sorry, D square, okay. And if there is a test charge, for example, then the force on it will be Q test times E, which is nothing but k q test times q d square. Okay, so these kind of forces, like this is the example of electric force, electrostatic force, ELE, electrostatic force. Okay. So it's a inverse square force. Okay, so the force is basically proportional to the inverse of the square of the distance. Okay, the distance from the source charge. That's why it is called the inverse square force. For example, you must have heard about the gravitational force. There also, if there are two masses separated by a distance d, capital M and small m, so then the force, gravitational attraction force, will be proportional to 1 by d square. Okay, if they are separated by a distance d. So these are all the inverse square forces present in our universe. Okay, or rather I should say the gravitational attraction or the electrostatic attractions and repulsions, they can be explained via these inverse square forces. Okay, so now if I write the potentials corresponding to that, say V, let me write it k tilde. Okay, potential at this point, for example, okay, at this point where the test charge is situated or located, so there the potential will be then some constant times q by d. Okay, because V is basically integration minus E dot ds. Okay, E dot ds, and so if I do the integration, it is basically if there is a, okay, if I do the integration, it will just be d. So if there is so here this d is basically distance, so that is the s, basically magnitude of s. So then it will be like ds square times ds, and s basically stands for d. I'm not writing d just because there is a d present here that represents the differential. Okay, then if I write d instead of s, then it will be like dd. I don't want to write that. Okay, so it will be, if I do the integration, it will be basically, okay, then it will be proportional to 1 by s. Okay, and that I am writing as d. S is d basically. Right. So in case of potential, we have this, right? And now if I write it like k q, okay, and d is nothing but mod of r minus capital R minus small r, so which is 1 by mod of capital R minus small r. Okay, and capital R minus small r square, if I do, so its mod is nothing but, let me write out, so mod of capital R minus small r is nothing but root under of capital R minus small r dot capital R minus small r. Okay, which is nothing but r dot capital R dot capital R, that is r square, okay, minus twice r dot r minus plus small r square. Okay, and what is r dot r? So if the angle between this small r and capital R vector is theta, then r dot r is r cos theta. So it is basically equals to root under r square minus twice r cos theta plus r square. Okay, and now if I write it kq times 1 by root under instead of mod of r vector minus capital R vector minus small r vector, if I write this expression, okay, it is minus 2i r cos theta plus r square, okay. And now if I take this r square outside of this root, then it will be divided by r, okay, will be 1 by root under 1 minus 2i r by r cos theta plus r by r whole square, okay. And now if I assume that, okay, now I am assuming that this r, or rather just r, less than capital R, okay. So I will choose my origin near about this source charge. So if I assume that r less than equal to capital R, in that case I can write h, I can replace this r by r, by h, okay. So let me define h in that way, and obviously h will be less than 1 in that case, and our x, let me call it, so let me call our cos theta is x, okay. And if I do that, then our potential will be nothing but k q by capital R times 1 by root under 1 minus 2hx plus h square. And if you can remember this quantity, this is nothing but the generating function of Legendre polynomial, that is h comma x, okay. Or it can also be written as kq r phi. What is h? H is r by r comma cos theta, x is cos theta. And now if I replace it, so if I replace this, so we know that, okay, this phi is basically, this generating function is basically sum over of, so phi of hx is basically sum over of plx h to the power l equals to 0 to infinity, okay. If I replace it, then we will get basically v equals to, v as a function of r v as a function of r theta, let me write it v, just is k q divided by r times sum over and what is h? H is our r by l, r by small r by capital R to the power l, and pl, what is x? X is cos theta, l equals to 0 to infinity. And now you can make sense of why we are so interested in in the fact that, or in the requirement that at x equals to plus minus 1, the series, we should get a convergent series, because whenever we are applying it in real problems, we are getting like pl cos theta, right? And this cos theta can take values like plus minus 1, okay. So in realistic problems, we must accept those solutions for which at x equals to plus minus 1 the series will be convergent, okay. And this is I can take this r, capital R, inside also, and then v will be sum over, oh sorry, it's k q l equals to 0 to infinity r by r to the power l divided by uh, small r to the power l divided by capital R to the power l plus 1 pl cos theta. So basically any inverse square potential, this I showed for electrostatic potentials, but also in case of gravitational potentials and all other inverse square potentials. This potential, for inverse square forces, the potential can be written in terms of the, in terms of the Legendre polynomials. Okay, and these are usually, this capital R are usually, if I take much greater than small r. Okay, so if our origin is so near, very near about this source charge, and we want to know about the effect of the source charge very far away from the origin, in that case, so that is the r and this is the smaller. So in that case, in those cases, basically this term this term will be very less than 1. This term will be much less than 1. Okay, and the higher we take this L, so if I take L equals to 1, 2, 3, 4, the higher values of L we go, then it will be much more, I mean, its value will decrease rapidly, and in that case we can approximate our this potential by a few Legendre polynomials like p0, p1 we can take, and then rest we can omit because of this factor present. Okay, which exponentially goes to 0. Okay, so this is one application of this Legendre polynomials. And so here I have considered about a single charge. Okay, here what I considered is basically, let's say this is our coordinate system, this is our origin. Okay, and there is a single charge, and here let's say at far away we want to measure the effect of that charge, and this is our small r. Okay, this is a single charge. Now let's say instead of a single charge we have many such charges. Okay, we have many such source charges distributed at distances. So qi, let's call them qi's, and I can go from 0, 1, 2, 3, 4, 5, and there are n point charges, and the distance they can be I can call it as ri's. Okay, so qi at a distance ri from the origin, and for all these charges we want to know the potential at this point, okay, where the test charge is located. So in that case it will be basically, our v will be basically k times sum over all i's, and there will be qi. So then there will be, so it will be basically qi times sum over l equals to 0 to infinity ri to the power l, ri to the power l, smaller I to the power l, capital I r to the power l plus 1, and pl cos of theta I. Why theta I? It's because depending on this charge, the angle, okay, depending on where that this qi located, this angle theta I, it will change, right? If qi1, let's say q1 is located here, then theta 1 will be this angle, right? For example, let's say if q1 is located here, and here we want to measure the effect, then this will be theta 1, right? And if q2 is located here, let's say, then this will be theta 2, right? So theta will also be like theta I will be, so depending on the source charge, whatever we are choosing, theta I will also change. That's why I need to put theta I also. Okay, so these are for discrete charges, and instead of discrete charge, if we have a distribution of charge, okay, so if, let's say there is a charge distribution, okay, in 3D, and we want to know the effect at a point far away. Okay, this is a capital R. So then how should we write it? So let's say for that, what we need to do is we need to consider a small, small volume of charge, infinitesimal volume of charge, okay, at a distance r, for example. Let's say a infinitesimal volume of charge. Let me call it dq. Okay, infinitesimal amount of charge, and it is located at a distance r, right? So in that case, dv, the potential because of this charge at this point will be k integration dq, okay, sum over of L equals to 0 to infinity r to the power L, capital small r to the power L, capital R to the power L plus 1 PL cos theta. And this is a volume charge, okay, then this integral is basically a volume integral, and this dq I can write also as rho times dv. Okay, if dv is the volume of this region, so then the charge will be charge density, this rho is charge density times dv. Okay, then it can be replaced as k rho dv, and this volume integral, the sum over L equals to 0. This for dv, this integration will not be there. So let me repeat it again. We want to know this effect of the small charge. Okay, so then it will be the small charge dq and times the all other factor, that will be dv, right? And that will be dv. So dv is the potential because of the small charge. Now if you want to know the effect of this potential of this entire charge, entire this discharge distribution, so what you need to do is we need to do the integration over this charge distribution. So this is a volume integral over this volume. So then it will be v, and so I should not write it v because it might get confused with this potential. So v I am using to denote the potential. So let me write it as tau. Okay, so tau denotes the volume integral. Tau denotes the volume basically. Then I should write it as d tau. Okay, this is, so dq is basically rho times d tau. D tau is the infinitesimal volume. Okay, and rho is the charge density. Density times volume is the basic total charge. So then our potential will be, because of this entire charge distribution, will be rho d tau over all this volume. Okay, this is a volume integral. Okay, that means it's a triple integral, r to the power L, r L plus 1 PL cos theta. Okay. So for a continuous charge distribution, this is the potential. I can write the summation sign outside also, L equals to 0 to infinity k. Okay, I can write this r to the power capital R outside of this integration also, because it's a constant. Okay, here the integration is over smaller, because the smaller will be changing and covering the entire source charge region. So I can put this k also outside, and it is integration over the volume. You can also write it as triple integral, because it's a volume integral. It should contain 3 axes, x, y, z, or r, theta, phi, whatever coordinate you choose. So d tau r to the power L PL cos theta. Now if I write a few terms depending on L equals to, for example, if I expand it, so the first term is for L equals to 0th term. The L equals to 0th term is basically k. If I put L equals to 0, then it is r triple integral tau volume integral rho d tau, okay, times r to the power 0. R to the power 0 is nothing but 1, and this p0 cos theta, and p0 cos theta, and p0 cos theta is nothing but is 1, right? P0 cos theta, P0x is 1. So this is the 0th term, L equals to 0th term. Now L equals to 1th term is basically, if I put L equals to 1, that is k by r square, okay, triple integral tau rho d tau r, okay, L equals to 1, that is r, and P1 cos theta, P1 cos theta is cos theta, right? So P1x is basically x, that means P1 cos theta is cos theta, r cos theta, plus higher order terms, okay, but of the order of L equals to 2 and higher order terms, right? And now if you look at this, what is this? Rho dot d tau, rho d tau, and that integration. So rho dot d tau, rho d tau is the dq, so infinitesimal charge. And if I integrate it over the volume, that means if I sum all the dq's over the volume, what do we get? We get total charge, right? This is basically the total charge, total source charge, right? Or let me write it total charge, okay? So the first term is basically k by r q total, okay? So for example, if you have q total charge at a single point, then actually you can see at a single point and at the origin, then basically you can approximate it, or then the potential at this point will be this kq total divided by r, right? So this is like a monopole term, where I can assume that all the charges are concentrated at the center, at a point, okay? And also another argument is, let's say r, this capital R is very large. In that case, we can neglect all other terms and we can only concentrate on this first term. In that case, the potential is behaving like the charge, total charge is concentrated at the origin, okay? So it means like if our test charge, or if you want to know the potential or the field at a very far away point, okay, in that case, this point will see this far away source charge as a single point charge, because it's very far away, so it will not see the distribution, it will see a single point charge, and that's what we are getting here. The first term basically says that, okay? And the second term, if I write, which is k r square volume integration of rho d tau r cos theta, this is basically a dipole term, okay? So this is a monopole term, this is basically a dipole term. So whenever you learn about the electrostatics, you will see these dipole terms. There will be the higher order terms will give you the quadrupole terms, octupole terms, and all. Okay, this is coming from P1 cos theta. Okay, so P1 cos theta is giving us the dipole term. Okay, this is basically the dipole moment, and this is r square. So whenever you will calculate the potential due to a dipole moment, you will see there will be r square sitting in the denominator. Okay, so it is basically charge times distance. This, you can see this rho d tau is basically the charge, dq times the distance. Okay, so it is basically the dipole term. And now if I took the next term, then it will be the quadrupole term. Okay, quadrupole term. If I take the another term, it will be the octupole term. So it will come from P2 cos theta. The next term will come from P3 cos theta. Okay, it will give me the octupole term, and then there will be higher order terms also. Okay. This is how the potential in a because of a inverse square force, those can be written in terms of the Legendre polynomials. It's a very important application, and whenever you will be learning this electrostatic force, electrostatics, and this gravity, then you will apply these Legendre polynomials, right? Okay, so that's all for the application part. Let me briefly uh, let me give you some, little exercises. So homework, okay, homework is basically expand or write these given functions, or expand the given functions, sorry, expand the given functions. Okay, these homeworks that I'm giving, it will be very helpful for tomorrow's or the next class, okay, where I will be talking about the orthogonality of functions. Okay. Because functions, they don't have any direction, right? So what do we mean by orthogonal? What do we mean by vectors? So is there any notion of vectors in whenever you're talking about these Legendre polynomials? So also let me add that whenever we are talking about vectors in case of these Legendre polynomials, or there will be Bessel functions, there will be Hermite functions. So don't try to think in terms of direction or magnitude, okay? And how to think about them, that I will tell in the next class. Okay, you need to think in terms of some abstract notations, abstract formulas. And if you want to know more about these vectors, in general term, not in terms of directional magnitude, but in abstract sense, in abstract algebra sense, so in that case you need to take a course on linear algebra. I think there are lots of courses available online. Okay, so the homework is expand the given functions in terms of, or as a linear combination of, as a linear combination of Legendre polynomials. Legendre polynomials. Okay. So linear combination, what do we mean by linear combination? For example, if there are two functions like f1x, like there are two functions f1x and f2x, then the linear combination of f1 and f2x is basically alpha 1 f1x plus alpha 2 f2x. Or this alpha 1 and alpha 2, they are constants. Okay, so the given functions are, number 1 is 5 minus 2x, number 2 is 3x square plus x minus 1, okay, number 3 is x to the power 4, number 4 is x minus x cube, and number 5 is 7x to the power 4 minus 3x plus 1. And how to do that? So let me give you an example. Okay, so let me solve this problem 2, number 2, which is 3x square plus x minus 1. So here x has a maximum power of 2, right? So in that case, so if you recall, this p0 x is basically 1, p1x is x, p2 x is 1 by 2, 3x square minus 1, p3 3x is 1 by 2, 5x square minus 5x cube minus 3x, and so on, right? I'm assuming that you have already derived this p4x and p5x, okay, that I gave you as homework. Okay, so you can see here in this function x has a maximum power of 2, right? So then you should write it as a linear combination of alpha 0 p0x plus alpha 1 p1x plus alpha 2 p2x. Not anymore, not anymore, okay? Not anymore. Not p3x, p4x, they will not come because they have a maximum power of so for p3x it has a maximum power of 3, okay, which is greater than 2, okay. So just check what is the maximum power of the given polynomial or given function, and choose that Legendre polynomial which is the maximum power that is same as this given function, okay. And then take the linear combination of all the Legendre polynomials which are less indexed or which has less power than this one, and take the linear combination. And now if I do that, then basically 3x square plus x minus 1 equals to alpha 0 and p0x is 1, okay, plus alpha 1x plus alpha 2 p2x is half 3x square minus 1, right, which is equals to, so now I will put together the constant terms which is alpha 0 minus alpha 2 by 2, okay. So one constant term is this alpha 0, another one should come from this minus 1, and then I will write the terms which are linear in x, that is alpha 1x. There is only one such term here, and then I will write the terms which are quadratic in x, that is alpha 2 3 alpha 2 by 2 times x square, okay. And now I will compare the coefficients. For example, if I compare the coefficient of this x, then it will be alpha 1 equals to 1, okay. If I compare the coefficient of x square, it will give me 3 alpha 2 by 2 equals to 3, implies alpha 2 equals to 2. And if I then compare the coefficient of this constant term, that means it will be alpha 0 minus alpha 2, you already know, right? Alpha 2 is 2, so it is 2 by 2, that is 1. So alpha 0 minus 1 equals to minus 1, right? Minus 1, which implies alpha 0 equals to minus 2. So basically our given polynomial, that is 3x square plus x minus 1, okay, it equals to alpha 0 is minus 2, so it is minus 2 p0x plus alpha 1 is 1, so plus p1x plus alpha 2 is 2, so it is alpha 2 p2x, that is 2 p2x, okay? That's the answer. So why these are so important? It's because you can start thinking in terms, like this. For example, so we are saying that, okay, any polynomial that can be written as a linear combination of these Legendre polynomials. So it's something like, for example, if you are in 2D, you are in a plane, and you are given two independent vectors, for example I hat and j hat, then any vector in this 2D plane you can write it as alpha I hat plus beta j hat, right? So it seems like this any polynomials, these are like vectors in this function space, in the space of functions, and this p0x p1x, p2x, these are like linearly independent vectors, and with these linearly independent vectors, if I linearly combine them, I can generate any polynomial, any vector in that space. So start thinking in terms of that language. It will be very helpful for the next class. Okay. There is no sense of directionality here. So don't try to think in terms of directions. These are functions. P0x, P1x, they are just functions. Okay, so let me give a hint for this problem 3 also. Like problem 3. Problem 3 is we are asked to write x to the power 4 as a linear combination of these Legendre polynomials, right? So in that case, x has a power, maximum power of 4. So that will be P4. Okay, P4 will have, if you have found out what is P4, what is the expression of P4, then you will see that P4 has a maximum power of 4. In P4, x has a maximum power of 4. So it will be basically up to P4 we should write the linear combination, that is alpha 0 P0x plus alpha 2 P2x plus alpha 3 P3x plus alpha 4 P4x, okay, up to this. And then you need to compare the coefficients of different, like x to the power 0, or which is basically the constant term, x square, x cube, and x4, and then get the value of this constant. There are 4 constants, and if you so there are 4 constants, right? Sorry, there is p1x, sorry, alpha 1 p1x, okay, plus alpha 1 p1x. So there are 5 constants, like is alpha 0, alpha 1, alpha 2, alpha 3, and alpha 4. And if you compare these coefficients, there will be 5 coefficients, 1 2 3 4 5, right? So from them you will get the 5 equations, and you can find the value of 5 unknowns. Okay, unknown means this alpha 0, alpha 1, alpha 2, alpha 3, and alpha 4. So in this way you can write all these given functions as a linear combination of these Legendre polynomials. Okay, so do that, and in the next class I will talk about the orthogonality of these Legendre polynomials. Bye.